This video will demonstrate a computational imaging technique called extended depth of field. This technique uses multi-shot imaging to create a greater depth of field than is possible with traditional one-shot image acquisition. In any single image, depth of field is limited by the optical magnification and lens aperture size used. In many imaging applications, the depth of field may not be great enough to focus sharply on all objects in a scene. Conventional solutions for increasing depth of field, such as closing the aperture, come with substantial trade-offs such as decreased light and less resolution. The extended depth of field technique is particularly effective for samples that vary greatly in height or distances. The practical depth of field can be extended many times beyond what is possible in a single image. This is the final result using this technique. The left image is the result of the extended depth of field process, where the entire sample is completely in focus from top to bottom. The right image is the result of a traditional single-shot image capture, which has limited depth of field and therefore a large amount of blur. This section will go through the required hardware and show the real-time process. Several pieces of hardware are required for this technique. Fundamentally, some method is needed to move the focal plane so that a sequence of images can be captured at different depths. In our demonstration, we use an electrically controlled liquid lens, which requires no moving parts and can rapidly switch focus compared to manual or motorized lenses. Depending on operating mode and focal shift, switching times for this type of lens range from a few milliseconds to 15 milliseconds. A programmable LED lighting controller is also needed to manage the multi-shot image sequence. This device coordinates the timing of the light pulses with the camera exposures and liquid lens focal plane changes. Here we are using a sequencing controller from CCS known as the LSS2404. We are also using a Gardasoft TR-CL180 liquid lens controller to program the step heights of the lens. In addition, a CCS HPR2-150SW standard ring light is used to illuminate the samples. There are two demonstration samples showing both discrete focus changes and continuous focus changes. The total height of the samples is around 80 millimeters. The first sample, a stair step, shows the depths at which we are in best focus over the entire range. Our single image depth of field is intentionally set to be slightly greater than the separation between focal planes. In this way, we can achieve continuous focus over the entire depth range, as shown by the Lego sample on the right. The left side of the split screen shows the samples moving under the camera, while the right side shows the real-time images captured and merged together to the final all-in-focus image. The left image is the computed image, and the right image is the traditional single image capture. You can see when comparing the two images, there are no blurry features on the left, while the right has only a small portion of the sample in focus. The total processing time depends on factors such as number of focal planes, camera resolution, and processor speed. In general, acceptable performance is easily achieved with an ordinary PC and a moderate resolution machine vision camera. As you can see, during the multi-shot image capture sequence, the sample is moving through the field of view. Special techniques are needed to correct for this motion, ensuring a completely sharp image of even rapidly moving objects. The resulting merged image compensates for the motion of the sample and combines the sharpest pixels of each input image into one image with an extended depth of field. The final depth of field depends on the focal range of the chosen lens and the number of focus images taken. This demonstration had a lens with a focal range of 20 millimeters, and we captured 4 images, so the total extended depth of field is 80 millimeters. Because of the depth of field overlap, The output image is in continuous focus over the entire sample. Thank you for watching this short application video. When you have an imaging system with insufficient depth of field, think in terms of computational imaging for a better way to extend focal range.